All right, welcome back to Physics 2. We will be talking about light, which you know is a small portion of the electromagnetic spectrum. So in this chapter, we're going to talk about light rays. So we're going to be expressing light as a ray, and we will talk about the laws of reflection and refraction. And then the other part of this summary here that we're going to focus on is polarized light. Okay, so these are going to be the main topics that we talk about. And we're going to skip some. Okay, we're skipping some stuff here. So as a brief introduction, we're very comfortable with light, right? Our eyes are detectors of light. And we see all sorts of cool phenomenon with light. And we're going to be talking about the rules, the laws, the math that goes along with understanding all the cool phenomenon that we see with light. One cool phenomenon is when white light shines on a diamond or a glass prism, okay, or any kind of glass, even just like the glass of a window, you can sometimes kind of see like a rainbow show up. And so basically what's going on here is you have white light, and white light is composed of all the wavelengths of light, right? Everything from 400 to 700 nanometers. So you have white light of different wavelengths entering this diamond from air, and it's going to not only enter a different material, namely diamond, it's going to also hit these different facets of diamond, which are different planes at different angles. And so you're going to get the light of different wavelengths reacting differently to the index of refraction of diamond and also to these different angles of the interface between air and diamond. So we're going to basically be warming up to the branch of optics, where in the next chapter, in chapter 34, we will learn how these optical devices like cameras, telescopes, eyeglasses, and of course the human eye, how they work. So that's chapter 34 there. So this is a great video to watch. We're going to be treating light as a ray, okay? So what is a ray? A ray is a convenient way to describe or represent the direction of motion of light, okay? And so what we have been talking about previously is the fact that electromagnetic waves are made up of E fields and B fields, right? And those amplitudes of E and B were proportional to cosine theta. Or, cosine of, whatever was in the argument, right? A whole bunch of stuff was in there. And these wavefronts are essentially the peaks of the cosine. So it's like we're looking down at a cosine function, right? And the peaks are here. And we know that the direction of propagation is perpendicular to those peaks. So the rays here are going to be the direction of propagation, and certainly here at the wavefront, they're perpendicular. Okay, so we're going to be treating light as a ray now. And rays are just going to point out the direction of the motion of the light. So light can do two things when it interacts with an interface. Okay, and so an interface is just a separation between two materials. So light, when it interacts with an interface, it either reflects or it refracts, which means it transmits through the interface, tunnels through, okay? And we're going to look at both cases, but both of them happen at the same time for the most part. So there's many rays, right? Any kind of source of light is going to emit, an infinite number of rays. And on a very smooth surface, all those rays will move parallel to each other, strike the surface, and bounce off at the same angle. Okay, that's when the source is really far away. So, but what we're going to do to analyze the movement, or I should say maybe the direction of the ray, is we're going to pick one. And we're going to define some angles, okay? The incident angle, the reflected angle, and the refracted angle. But before we get into the angles, Let's talk generally about the types of reflection. So there's two types of reflection. There's the specular reflection, which is what we just talked about, right? The angle that the light that it makes with the normal after it reflects from a surface, they're all going to be the same for every ray because the surface is super flat, okay? Smooth and flat. But, as in real life, most of the surfaces are rough. And when light reflects off of these rough surfaces, it's called diffuse reflection. And it's diffuse because the outgoing, the reflected rays here, they all point in slightly different directions because everywhere that the ray, at every place that the ray hits, the surface is at a slightly different angle. So everything that we deal with coming up in this chapter is going to be specular reflection. Okay, we're going to assume that all the rays are going to bounce off at the same angle. So let's talk about the first law, the law of reflection. All right, so the law of reflection, pretty easy to understand. The angle of incidence, which is defined with respect to the normal, is going to equal the angle that the reflected ray makes with the normal. So these angles are equal. Angle of incidence equals angle of reflection. These are all measured with respect to the normal. And guess what? This is true for all wavelengths of light and between any pair of materials. So it doesn't matter what material A is and what material B is. This could be air, this could be glass, this could be glass, this could be diamond, okay? It doesn't matter. This is always going to be true. Okay, the law of reflection is pretty easy to understand. The angle in made with the normal is equal to the angle out, and these are all with respect to the normal. That's how we define these angles, okay? So let's just kind of look at this picture real quick. So the surface is going to be the interface between the two materials. So this is the interface, this is the surface, okay? It's vertical in this particular picture. The normal will be 90 degrees to that, okay? And then the angles will be defined with respect to the normal, right? Not too bad. We just have to be really careful about the definitions. So let's talk more about the law of reflection. Let's use it in practice. So this is your pre-lecture video. I have them kind of embedded in the lecture sometimes. And I want to do a problem from the pre-lecture video. And I believe I have that problem right here. And so in this problem, we're going to use the law of reflection. So let me delete, the work here. Oops, didn't want to delete all that. Fine, let me just erase. This was from my lecture, my in-person lecture. All right, so from your pre-lecture video, a flat mirror is used to illuminate the bottom of a deep well. Okay, I'm going to underline that. That's going to be a piece of information we need to translate to this problem. The sun's rays make an angle of 27 degrees with the Earth's surface. At what angle alpha is the mirror position? So we're basically going to find alpha given these two pieces of information. Okay, so how do we put these pieces of information into the problem? And where does the law of reflection come in? Well, so let's start with piece of information number 2. We're told that the sun's rays make an angle of 27 degrees with the Earth's surface. This is the well. This is going to be the Earth's surface, okay? So the incoming ray is going to strike the mirror and make an angle of 27 degrees. Let me see if I can... Does this look like 20? Oh, that looks close. That's close to 27 degrees, okay? This is 27 degrees right here. The angle that the incoming ray makes with the Earth's surface. And then piece of information number 1 is that this mirror is used to illuminate the bottom of a deep well. So this reflected ray is going to reach the bottom of the deep well. And we're not given any constraints here. So we can assume that the ray goes straight down and even overlaps this vertical line that is used to define alpha. Okay? So the difficulty of this problem was interpreting this piece of information, number one, into the problem. Well, if the mirror is used to illuminate the bottom of a deep well, then that ray that's reflected from the mirror should hit the bottom of the deep well, right? To bring light to it, to illuminate it, right? So now that we have those two pieces of information in our problem, let's apply the law of reflection to help us figure out what alpha is. So the law of reflection states that the angle of incidence equals the reflected angle. And these are with respect to the normal of the surface that it's reflecting off. So the surface is this mirror here, right? And so then the normal is going to be 90 degrees. Does that look like 90 degrees? Let's try to make it look like 90 degrees. 90 degrees from the mirror, okay? And so that means that this angle, theta, is going to be the incident angle. And then this angle is the reflected angle. Now, they don't look equal, but they are, okay? The only reason why they don't look equal right now is because they don't look equal because I didn't draw 27 degrees very well. Okay, it's probably a little bit bigger than 27 degrees. Not drawn to scale. Okay, but so we're just gonna have to use our imagination here. Those two angles are equal. And so if those two angles are equal, then their combined angle, which I'll draw in purple, is 2 theta, right? 2 theta I, if you will, whichever one, whichever theta, theta R, theta I, they're equal. So that combined angle is 2 theta. And so why do I care about that combined angle? Right up here. Because I can form a right triangle right here. And I can figure out what theta is, right? Because I know this is 90. I know this is 27. And then I have 2 theta here. So the first thing I can do is I can figure out what theta is. 2 theta plus 27 plus 90 must equal 180 degrees. And so then theta is going to be 180 minus 90 minus 27 all over 2. So that becomes, let's see, 90 minus 27 is 63 over 2, which is 31.5 degrees, right? Yeah, 31.5 degrees. So there's my theta. Okay, great. I found theta. Now what? Okay, well, I need alpha. And so we need to figure out how alpha and theta are related. So I'm going to use the fact that this red line here, right, this vertical line goes all the way through here. And if that's the case, and I extend this out, then this guy has to be alpha, right? And if that guy's alpha, this is the mirror, this is the normal, then this here is 90 degrees. And therefore, 90 must equal alpha plus one of the thetas, okay? And so then theta equals, oh no, we know theta. We want to solve for alpha. Oops, why is it deleting so much? Alpha is going to equal 90, sorry, that's my son yelling at the dog. Sorry for the background noise if you can hear that. So alpha is going to be 90 minus theta. So that's going to be 90 minus 31.5 degrees. Let me write this somewhere else. He just brought the dog in the room. Okay, dog, be a good boy. I'll have to show you some pictures of my dogs one of these days. So we're solving for alpha. Alpha is 90 minus 31.5. And so then alpha is going to be 59.5. Right? Let's see. That's 80, 90, 58.5. Oops. .5 degrees. There we go. That's how we did it. So these law of reflection problems, I mean, they're really just kind of like crazy geometry problems. All right. The law of reflection helped a little bit because we were able to combine those two angles into 2 theta since we knew they were equal. And of course they don't look equal because I didn't draw 27 to scale. So the shallower I draw, and that's why in that, if you saw earlier, I had it redrawn here. So if I extend the well base like this, and I put my mirror here, oops, my mirror was like this. My mirror is like this, okay. Then I needed to go farther back to make that angle 27. So there, that's maybe a little bit closer to 27. And then that would make this guy, oops, the vertical to go straight down. And then I draw my normal here. And there we go. It looks a little bit more like they're equal. See that? Now it looks a little bit more equal. All right, it's just because I didn't have that first 27 drawn to scale. So now they look very equal. All right, and then we just go on with the rest of the business here. So these law of reflection problems are just crazy geometry problems, okay? So, and then the other level of difficulty is translating what the given information is in terms of the problem. All right, so it's not too bad here. Before we get into the law of refraction, let's remind ourselves what the index of refraction is and what it means. The index of refraction of an optical material is defined as the ratio of the speed of light in vacuum, which is C, to the speed of the light in the material. Okay, so it's a ratio, it's an index. And the slower, or the smaller the V, right? The slower the light goes, the higher the index of refraction. Okay, so high index of refraction materials cause waves to move slower. Now, the closer V gets to the speed of light, so what I should say here is the closer that V gets to, let's see, as V approaches the speed of light, in other words, for a large V, we're going to have a small index of refraction, an index of refraction that approaches 1. And with small indices of refraction that are close to 1, you have a fast moving wave. So that's physically what's going on. So now let's look at the law of refraction. So the law of refraction states that the index of refraction of material number 1, A, it multiplied by sine of the angle of incidence is going to equal the index of refraction of material B times sine of that refracted angle. Okay, the angle that the light makes with the normal in that new material B. This is also called Snell's law. And this is basically the law that governs how light moves in a new material. Okay, when it transitions from one material to another. So if we look at this picture here, in the case shown below, material B has a larger index of refraction than material A. And that's because theta B is smaller than theta A, right? You can see it's a much smaller angle. And remember that theta is always defined with respect to the normal. All the thetas are. So let's do an example where we employ that and the law of reflection. So in this example, we have a material A, which is water, and material B, which is glass. So we have water sitting in like a glass jar or glass bowl. We're given the indices of refraction of both of those materials, and all we're told is the angle of incidence. So the angle of incidence is 60 degrees. What is the directions of the reflected and the refracted rays? So that's what we're going to figure out. Well, for reflected rays, we're going to use the law of reflection, which states that the incident angle, you know, they use A subscript. So we'll go ahead and keep that. The incident angle is equal to the reflected angle. So the incident angle is 60 degrees. That will also be the reflected angle. Boom, easy. What about the refracted ray? We're going to use Snell's law, which states that index of refraction, material A, angle of incidence in material A is going to equal index of refraction, material B, angle of refraction in material B. And so we're given an A as 1.33, sine of 60, 1.52, sine of theta B, solving for theta B. So we're going to do 1.33 times sine of 60. All of that is going to be in the argument of inverse cosine. Okay, and that's going to give us our refracted angle. So plug that in your calculator. Grab mine. Okay. Times sine of 60. And then we're going to inverse that. So let me just go ahead and write some steps. So that is sine -1 of about 0.758. And then we get roughly 49 degrees. 49.3 degrees. Okay, so that's our theta B. Okay, so not too crazy. When you get a problem like this in your homework on the exam, you're not going to have all these, all this drawing is going to be missing. And basically all you're going to be given in the problem is something like this. Okay, here's material A, here's material B, figure it out. So you'll need to read the problem and identify the interface, okay? And then identify the normal to the interface. And then identify the incoming angle as being this one right here. And then the reflected angle being this one right here. The refracted angle being this one right here, okay? So it looks simple now in the example because this picture has everything you need. But in the homework and on the exam, you won't have that picture, okay? You'll have to draw it. So that's part of the difficulty level. So just to summarize what we just discussed, right? 2 laws. Law of reflection, easy. Angle in is angle out. Of course, these angles are defined to the normal. Second law, Snell's law, which is the law of refraction. And there you multiply the angle, the refractive index multiplied by sine of the incident angle times the refractive index of the second material times the refracted sine of the refracted angle. Okay, and of course these angles are measured with respect to the normal. So let's kind of look at some cases here. All right, we're going to physically talk about what's happening to that light as it enters in a material. So when the ray of light passes from material A to material B, and the index of refraction of material B is greater than A. So for example, this one might be 1.5 and this one might be 1.2. Well, what happens is the light's going to slow down when it gets to material B, right? It's going to slow down. And the angle theta B is going to be smaller than theta A. Okay, so theta B is going to be less than theta A. All right, case number 2. What if the index of refraction in A is bigger. So what if this one's 1.5 and this one's 1.2? Well, when the incident ray meets this interface and becomes transmitted, it's going to start to go faster. And when it moves faster, the refracted angle is going to be larger than the incident angle. So theta B will be greater than theta A if NA is greater than NB. Okay? So finally, a third case. What happens if theta is 0? Okay, well, if theta is 0, then sine of theta A is 0. And then so theta B must also be 0 because N cannot be 0, right? So if we write this out, if this term is 0, we know that N can never be 0, right? The lower limit of N is 1. That's the smallest N could ever be. So that must force this to also be equal to 0, okay? Which means that the refracted ray is either 0, like, you know, when is sine of the angle equal to 0? It's equal to 0 when either theta is 0 or theta is pi, right? Which would correspond to theta being 0 would be pointing the ray pointing this way, and theta equals pi would be pointing this way. So a ray that is oriented along the normal does not bend, okay? It's either transmitted or reflected depending on the values of NA and NB. All right, so those are the cases. So now let's talk a little bit about the wavelength, one in particular, and what's happening to it as it goes through different indices of refraction. So let's talk about yellow light, which has a vacuum wavelength of 589 nanometers. Well, when yellow light goes through ice, it's going to move faster than it does when it goes through diamond, which has a high index of refraction. Okay, and that's basically how you interpret the index of refraction. So light moves slower in high indices and moves faster in indices closer to 1. So if the frequency remains the same, right? Remember that from the last chapter discussion. If the frequency remains the same and the speed is changing, well, in order for this equation to remain true, the wavelength must change as well. Okay, so the wavelength changes as light enters a new material. So let's kind of understand that. Where does this equation come from? Let's do like a mini derivation. So recall that C, the speed of light in vacuum, is equal to the wavelength of light in vacuum times its frequency. And then the velocity of a wave in some other material is equal to its wavelength in that material times frequency. If I divide both sides, the left-hand side becomes n, right? And the right-hand side becomes lambda naught over lambda. And if I rearrange that to solve for this new wavelength in this material of index of refraction n, we see that lambda equals lambda naught over n, which is this guy right here. Okay, the wavelength of light in a material. So the wavelength changes depending on what material that light is in. Okay, not just light, but any electromagnetic radiation. So physically, what's going on? Well, we can think about it as when a wave passes from one material into another, the wave gets squeezed if the speed decreases. So basically, lambda decreases as the speed decreases, and lambda increases or stretches as the speed increases. Okay? So that's physically what's going on. So the wavelength does change of the wave. However, the frequency does not, because why? The frequency of the electromagnetic radiation that comes from the source. That is something that is given to the wave from the source, and that can't be taken away. So let's do this example where we kind of use that fact. So when we characterize colors with wavelength, we characterize them in terms of their vacuum wavelength. So when we say red light has a wavelength of 633 nanometers, that's the wavelength of red light in vacuum. But as you might already know, your eyes are not made of vacuum, are they? They're made of like weird biological jellies, okay? And so when light penetrates that jelly, it actually changes its wavelength, okay? For example, when red light of wavelength 633 nanometers enters the aqueous humor of your eye, it becomes 474 nanometers. So using that information, using the fact that the vacuum wavelength of red light 633 enters your eye at 474, what is the index of refraction, the speed of the wave, the light wave, and the frequency of the light? So using the previous equation, we saw that the vacuum wavelength divided by the index of refraction gives us the wavelength of light in that material. So we can rearrange this, okay? And so the index of refraction is going to be 633 divided by 474. And that's going to be 1.34. So what about the speed of the wave? Well, we know that the speed of the wave equals its wavelength times its frequency, but we don't know the frequency yet. So we also know that the index of refraction can be defined in terms of the speed of the wave. So let's use that. We know the index of refraction is 1.34, and we know the speed of the wave in vacuum is the speed of light. So all we're doing is solving for V here. So V ends up being speed of light divided by 1.34. And that comes out to be 2.24 times 10 to the 8 meters per second. And so finally, we need to find the frequency of the light. Well, recall that the frequency of the light doesn't change from vacuum to eyeball jelly, okay? So we can use either equation. Since we know both C and V, we can use either equation to find frequency. So let's just use the vacuum equation. So F is going to be C over lambda naught. C is 3 times 10 to the 8. Lambda naught is 633 times 10 to the minus 9 meters. Okay, so our frequency is going to end up being a very big number. 3 e to the 8 divided by 633 e to the minus 9. It's going to be about 4.74 times 10 to the 14 hertz. So that, just because I am familiar with the electromagnetic spectrum, to me, 10 to the 14 hertz tells me it's a color, right? It's a light in the visible range. So that checks out. And you can always check your electromagnetic spectrum just to make sure you're in the ballpark. But to me, I recognize that. It looks good. Okay, so nothing too crazy here. So the concept here is mainly the index of refraction, right? When the light is in a different material, the frequency remains the same, but the wavelength and the speed change. Okay, and they change according to these two equations. Okay, frequency stays the same. So let's kind of like take a step back. Let's go back to the law of reflection and do this example. Let me hide a bunch of stuff here. Okay, so that we don't see all the answers. And anyway, it gets very confusing. I mean, it's kind of like the way I do it, I think. maybe makes more sense. I don't know. We'll see. We'll see what makes sense to you. So let me erase some of this stuff here. All right. And so we're starting off with the givens. The given is that we have two perpendicular mirrors. All right. So that means they're in an L shape. They're perpendicular to each other. And that we have a ray traveling from, you know, an area outside of the mirrors to mirror one, bouncing off of mirror one, bouncing off of mirror two, and then leaving the area. The question is, what is the ray's final direction relative to its original direction? So we're going to use the law of reflection here to help us figure out how this ray, well, that's very big, how this ray right here, its direction compares to this one here, okay? So when the ray first meets mirror one, it's going to reflect off of mirror one, and we know by the law of reflection that the incident angle is going to equal the reflected angle. So therefore, we're going to call these both theta 1, and that's, of course, defined with respect to the normal, right? This is the normal right here. And it's going to bounce off of this mirror. And so what angle is this, are these going to be? Well, if we draw our normal, whatever we decide to call these angles, let's call them theta 2, they're going to be equal. And so the crux of the problem is we need to describe basically theta 2 in terms of theta 1, okay? To try to describe the direction of the ray, the exiting ray, relative to its original direction. So we need some geometry here to connect theta 1 to theta 2. And right off the bat, I'm seeing something here. I'm seeing a right triangle. All right, I'm seeing a right triangle made by the two normals of each mirror. And so we can see how theta 2 is connected to theta 1. So basically, 90 must equal theta 1 plus theta 2. Do you see that? Because the whole triangle must add up to 180. This guy's 90, so the other two must add to 90. And so if we know that 90 equals theta 1 plus theta 2, how does that help us out here? So what we need to do to see the direction of this ray relative to the first ray, the incident ray, is let's add up all the angles between those two rays, meaning let's add up theta 1 plus theta 1 and theta 2 plus theta 2. So let's convert, let's talk about basically one angle, okay? So let's express theta 1 as 90 minus theta 2, and let's add all these angles up. So if we're adding the angles, what we see is that we have theta 1 plus theta 1 plus theta 2 plus theta 2, right? So theta 1 is 90 minus theta 2. We have another 90 minus theta 2, and then we're adding theta 2 back. So it looks like our theta 2's go away, and all that we're left is 90 plus 90, which is 180. So the angles between these two incident and reflected ray is 180 degrees. And what does that tell us? That tells us that they are parallel. Parallel. Can't spell today. Parallel. Okay. Well, technically they're anti-parallel, right? Because there's a directionality associated with them. So they're anti-parallel. The angle between them is 180 degrees. All right. So the final direction relative to the original direction is that the reflected ray, so the answer, I guess, and described as questioned, is the reflected ray is 180 degrees opposite to the incident ray. All right, so these questions that deal with the law of reflection. I mean, they are all geometry questions, all right? They are, the geometry gets a little bit weird sometimes. So brush up on that to help you out with questions relating to the law of reflection. So, I guess I have this video sort of out of place, right? There's some good practice problems in this video, so definitely take a look at those. The last thing we're going to talk about in this lecture is polarization. So we're going to bring back up the fact that light is an electromagnetic wave and it has an E field and a B field, all right? But we're going to focus on the E field. And so polarization refers to the orientation of the electric field vector in an electromagnetic wave, okay? And so when an electromagnetic wave is polarized, or if it's linearly polarized, that means that the electric field has only one component, okay? Which is like it's either all on the x-axis or maybe it's all on the y-axis, okay? And light can also be unpolarized, okay? Natural light is unpolarized light. So if light is unpolarized, what does that mean? Well, unpolarized light has electric field vectors that are pointing in all directions randomly. Okay, so it has the E field has every component. And some examples of unpolarized light is light from a traditional light bulb. Traditional light bulb. Polarized light is very prevalent in today's world. For example, sunlight is polarized. And nowadays, most of our light, instead of coming from a traditional incandescent light bulb, comes from LEDs. And LEDs are also polarized. Okay, so natural light, unpolarized light, sunlight, those are all meaning the same thing. Those mean the electric field vectors, they're random. Okay, they're pointing in every possible direction. Okay, there isn't one particular direction. And so, how do we polarize light? Well, we can use materials. So we've been talking about light interacting with materials. So when light transmits or refracts through certain materials, there can be a polarization effect. And the polarization effect is the fact that the material absorbs the E field vectors in every direction except the polarization axis, okay? So in this picture here on the right, you see unpolarized light, which has E field pointing in every direction, perpendicular to the propagation direction, of course. It enters the polarizing filter, and the E field in every other direction gets absorbed in there. And all that comes out are E field vectors that are parallel to the polarizing axis, okay? So that's what happens when light enters a polarizing filter. It becomes polarized. So if we are taking away a bunch of E field vectors out of an electromagnetic wave, and recall earlier in the previous chapter that the intensity of an electromagnetic wave is proportional to the square of the E field. If we're removing a lot of the E field, what do you think happens to the intensity? It goes down, right? So Malus's law tells us how the intensity of the light decreases after it passes through a polarizing filter. And so we need to examine two cases. The first case we need to examine is what happens when unpolarized light enters a polarizing filter. Well, we already know what happens to the E field vector, right? What happens to it is all the other vectors go away except for the one that is parallel to the polarizing axis. okay? So the intensity decreases in this situation by a factor of 2. So the intensity after passing through a polarizer is the original intensity over 2. And this is for unpolarized light. So where does this factor of 1/2 come from? Well, it comes from Malice's law down below. So let me explain to you Malice's law, and then I'll go back and tell you where this 1/2 comes from, okay? So let's look at the second case. The second case is when light that's already polarized enters the polarizing filter. And when light that is already polarized, meaning it already has an E field pointing in a particular direction, okay? When it passes through a polarizing filter, the intensity reduces by a factor of cosine squared of the angle between the E field vector and the polarizing axis, okay? So this theta here, or this phi, little lowercase phi, is the angle between the polarization axis and the axis of the analyzer, okay? So the intensity decreases by a factor of cosine squared of this angle difference. So now let's think about this. If light is unpolarized, it has an infinite number of E field directions, right? So to calculate the intensity, we would have to do this cosine squared angle between a bunch of times, right? We would need to get the angle between this and this axis. We would need to get the angle between this vector and this one. We would need to get the angle between this vector and this one. And so we would be doing that a million bajillion times. Well, how about instead of doing that, because that would take forever, we're going to average the cosine squared function and find the average for all these delta thetas, okay? These delta phi's, if you will, these right here. And so what you see is that if you have a cosine squared function of some angle, well, remember cosine squared lives above the 0, right? So if this is normalized by 1 and this is 0, that's a cosine squared function. The average value of that is this right here, this value right here, which is what? 1/2, right? You have just as much cosine squared above as you do below. The average value of cosine squared theta is 1/2, and that's where this 1/2 comes from, okay? Because we're finding the angle between all the different polarization directions and the analyzer, okay? So instead of doing that a million times, we're just going to find the average value. So when you're using Malice's law to find the intensity change due to light entering a polarizing filter, you need to first decide or determine, is that light initially unpolarized or is it already polarized? And then you'll use one of these two equations here. Okay, so that's kind of the trick to that. So let's do this example. Let me erase all this stuff here. I colored over, there's a picture here, but I didn't like the picture. I thought maybe it was going to be a little bit too confusing. So let me just show you what I mean. Like, here's the picture I put here. And that's the picture that it refers to in the problem. But I thought maybe it'd be a little bit confusing. So let me go ahead and cover up this picture again. And we'll draw the picture ourselves. Okay, because a lot of these questions on the exam and stuff, you won't get a picture. So let's start off with no picture. All right. So we have unpolarized light. So we're starting off with unpolarized light. So what does that mean? We have like a bazillion different E field vectors for our light. And the intensity of that unpolarized light is I naught. Find the intensities transmitted by the first and second polarizers if the angle between the axes of the two filters is 30 degrees. So we have two polarizers here. okay? And the angle between them is 30 degrees. So, well, what I could do is I could just make the first polarizer have an angle that is vertical, and then the second one would be 30 degrees to that. Because what you'll see is that the angle, you know, between the two is what matters the most here, okay? So, so let's calculate what the intensity changes after the unpolarized light passes through polarizer number 1. Okay, and what does that light look like? Let me just extend my white down here a little bit. And I'd like to move this thing. Let's move it over here. So the unpolarized light, so here we have the case of unpolarized light entering a filter, right? And it's going to go, and it's, you know, going along the propagation direction, which is to the right. Oops. Okay. And let me kind of like draw that through the middle here. So the intensity of the light after it passes through polarizer 1, that's going to be given by, I'm going to call that I1. It's going to be, well, it's just going to be I naught divided by 2. And what's that light going to look like? Well, it's going to be polarized after it comes out of polarizer 1, right? And it's going to be polarized in the same direction as the polarization axis of polarizer 1, which I've denoted by the black line. So the light is going to come out looking like this, okay? It's going to be polarized in the same direction as polarizer axis 1. And so now let's look at, it's going to encounter the second polarizer, okay? And so what's the intensity after that? Well, it's going to be the initial intensity before it reaches polarizer 2, which was I1, times cosine squared of the angle between the E field and polarizer 2 axis, which is, where am I? Okay, here. Oh, I just don't know where I was going here. I was going to try to make this a little bit bigger. Need some more room. So cosine squared, the angle between this guy and this axis, which is going to be 30 degrees. And you can see how that was described in the problem. In the problem, that was described as the angle between the two filters. But now you can see that the E field vector picked up the angle of the first filter, so you are given essentially the angle between the E field vector and the second filter. So, well, we need, since I naught is what was given to us, we need to express I2 in terms of I naught. So I1 is equal to I naught over 2, and then all that times cosine squared 30. And that becomes, so cosine of 30 squared ends up being, it's 0.75. So that becomes I naught over 2 times 3 over 4, right, which is 0.75. So that becomes 3/8 I naught. So, so the intensity after the first polarizer is I naught over 2, and the intensity after the second polarizer is 3/8 I naught. Okay, so that's the idea. You know, just be careful if you are starting off with unpolarized light or polarized light. All right, that's how this problem could change. And so that is the end of chapter 33. Okay, so we just touched on a couple of sections in chapter 33. So go work on that homework and, you know, do all the extra credit. And we will pick back up next week with the final chapter in the course, okay?